Now let's see this next form of normalization, which is Bcnf. Till now we have seen till third normal form. So till third normal form is not really enough to eliminate more redundancies. Initially when this Bcnf was proposed, it was actually proposed as a lighter version of third normal form, but later it turned out to be more strict compared to the third normal form. I'll just tell you why. And third normal form is not going to eliminate all the redundancies compared to Bcnf. That is why we are going for Bcnf. Let me tell you the difference using an example and the definition. So the definition of Bcnf is like this. A relational schema capital R is in Bcnf if whenever a non-trivial FD X determines A holds in R, then X is a super key of R. That is, determinants of all functional dependencies must be super key. So if you see this definition, it is exactly similar to the third normal form definition, formal definition of third normal form, with one difference. In third normal form, if you remember it, there are two conditions. If you have a functional dependency X determines A, and if it is holding on the relation capital R, then capital R is in third normal form, given that either left side is a super key or right side is a prime attribute. Got it? But now coming to this definition, see, first condition is what? Left side, which means X is a super key, right? Or what is the second condition? A is a prime attribute, right? Now coming to Bcnf, we are not going to have the second condition. If a functional dependency X determines A holds on R, then R is in Bcnf only if X is a super key. Got it? Which means so if you see this, we are not asking third normal form to satisfy these two conditions. We are asking the third normal form to satisfy only first condition in any of these conditions, right? Which means, see, in third normal form we are giving them two options. Either you satisfy this or satisfy this. But in Bcnf we are giving them only one option. You have to definitely satisfy this, otherwise you are not going to win Bcnf, right? So if you observe it, Bcnf is going to be more strict compared to the third normal form. So what I mean to say is, there can be relations which are in third normal form but not in Bcnf, right? But then there cannot be relations which are in Bcnf but not in third normal form. So every relation which is in Bcnf will be always in third normal form. So if you try to see it in a diagram, don't get confused here. So you might get confused that, since there are two conditions given for Bcnf and only one condition given for Bcnf and two conditions given for third normal form, you might think that third normal form is more strict, but then Bcnf is more strict compared to third normal form. So if you want to see it, the relation between Bcnf and third normal form, you can write like this. So if you have third normal form here, Bcnf will be here, right? Now if a relationship falls here, then it means that the relation is both in Bcnf as well as in third normal form. But if a relation falls here, then it means that it is only in third normal form but not in Bcnf. Therefore, there can be relations which can be third normal form, which can be in third normal form but not in Bcnf. But then there cannot be any relation which is already in Bcnf but not third normal form. Why? Bcnf is already stricter than third normal form. See, don't think that this subset. Okay. So what I mean to say is, Bcnf is strict compared to third normal form. Got it? So what is the main difference between Bcnf and third normal form is, if you see this example, you will understand it. Let us say there is a table ABC, right? Now if you see this these two functional dependencies, now Bcnf says that whenever you have a left side of functional dependency, it should always be a functional the super key. Got it? Every left side of the functional dependency should always be a super key. That is what Bcnf says. But our third normal form says that either the left side should be a super key or the right side should be a prime attribute. Therefore, according to that definition, the table ABC will be in third normal form. Why will it be in third normal form is, if you see it, the keys are going to be, one is AB and other is AC. These are the two keys, candidate keys for this table, AB and AC. Now if you observe it, AB is a super key, but C is not a super key, but B is a part of the key, which means it is a prime attribute. That is why, according to the third normal form, even though these two FDs hold on this relation is still in third normal form, but it cannot be in BCNF. The reason is BCNF says that only one condition has to be satisfied. That condition is every left hand side of the functional dependency should be a super key. Yes, this one is super key, fine, but then this one is not the super key for the table. Got it? That is why you are supposed to decompose it, right? Now how does this one eliminate the redundancies is, you can take this example. Look at this example. Now AB determines C, that holds definitely for every value of AB here. C is going to be same, which means if 0 1 is there, for any other instance occurrence of 0 1, C is going to be 1 itself, right? Anyway, since AB is a key here, 0 1 is not going to repeat, right? So AB determines C is going to hold on this. Along with that, C determines B is going to hold. So what does it mean? For any value of C, for any repeated value of C, B is going to have the same value, right? So now if you see this here, see this entire thing, C determines B is holding, therefore whenever C is 1, B is 1. See this, whenever C is 1, B is 1. Now if you look at this, maybe if you try to divide it into separate tables, then this redundancy might be avoided, right? So that is where BCNF is going to help us. So according to third normal form, we are not going to decompose this table, but if you try to decompose it according to the BCNF, then even this redundancy can be eliminated, right? Now if you see this, the decomposition, see, only because of this one, only because of this functional dependency, this table is not going to be in functional, BCNF. What is the reason? The left side of the functional dependency is not a key, super key. So now that is why I am trying to decompose it, right? So how can I decompose it? Take C and apply closure, then you are going to get CB. Got it? Therefore, I want to separate out CB into one table, right, with C as the primary key, and on the other table I am going to keep AC, right? Now we don't know, there is no relation saying that A is determining C or C is determining A. Therefore for this table, entire AC is going to be the candidate key. Now I have used this decomposition, right? Now I am going to write AC in one table and CB in another table. Now if you see this, AC, for A 0, B, C is 1, for A 1, C is 2, right? For A 1, C is again 3. See this, these are repeating, that is why A cannot be the key. So the key is going to be AC. AC, entire thing has to be key. See, whenever you don't have any key, you are going to take the entire relation as the key, isn't it? See, the functional dependencies are not saying that either A can be key or C can be key. That is why what we do is take both A and C as the key. Now since A is repeating, that's not an issue. A and C together should not repeat. That is the only condition. Okay. So for 1, 2, 1, 3, for 0 it is 4, and for 4 it is 1, and for 5 it is 1, for 6 it is 1, for 7 it is 1. Yes, this redundancy you can't do anything about it, right? But now look at this one for C and B. Now whenever C is 1, B is 1, therefore this entire, all the values of B can be represented in just one value. Got it? So whenever C is 1, B is 1, that is over, right? And whenever C is 2, B is 1, C is 3, B is 0, 4, 0. That's it. This is the table. So this entire redundancy can be eliminated. Got it? So if you see this, that entire redundancy has been kept in one step. But there is a small problem here. Even though we are able to eliminate redundancy more compared to third normal form, if you see the functional dependencies that are applicable on both the tables, on this table no functional dependency is applicable, on this table only functional dependency applicable is C determines B. That's it. Therefore we are never going to get this. If you see C determines B, will never be able to cover AB determines C. If you try to find out AB closure here and C closure here, you will see that you are never going to cover this. Got it? So what can we say? You are going to lose this functional dependency. That is the problem with BCNF. In BCNF, the redundancy is going to be reduced, but then the functional dependencies may not be preserved. That is it. That is the problem here, right? So some questions possible on this will be, okay, you might think that maybe in this way we have decomposed it, that is why the functional dependency is not preserved. If you try to decompose it in some other way, it may be preserved. You try it in any other way, you try to decompose it in any other way, you take two of them here and two of them here, keeping only one in the intersection, you will always see that this one will not be preserved. The reason is, if all the three attributes are not going to be there in this example, in this particular example, you can never preserve this. With two attributes in one table, you can never preserve this. Therefore, it can never be preserved. But then one thing is for sure, the lossless decomposition is still there. See, whenever we decompose, our top priority is to see that it is always lossless. Why? Because when we join the tables, we don't want to lose the information. Lose the information in the sense, we don't want to create more spurious tuples. So creating two spurious tuples is nothing but losing the information, which means getting extra information is nothing but losing the original information, isn't it? So now if you see this, the intersection is C, and C is a key attribute for one of the tables, so it is enough. So this decomposition is definitely lossless, fine, but then the problem is FDs are not preserved. So with more examples you will see the cases. Okay.